This doesn't
This
seem
one,
to be
yeah,
doing anything.
There, we'll just use like this one. Yeah, so
Sometimes if you go out of the PowerPoint
I got
and just
you.
kind of.
All right.
okay.
At it.
We're good. Look at that.
How many PhDs?
Multiple PhDs and the slides are working, at least temporarily. Okay, so to remind ourselves, if we want to go into space for any period of time where we're not going to be resupplied from the Earth frequently, we're going to want plants. And why do we want plants? This is what you remember from 8th grade biology, because plants are uniquely able to take carbon dioxide out of the air, take light from the sun or any other source, and from that, fix carbon, basically make food for us and produce oxygen that we need to breathe. And so by doing that, they clean the atmosphere of the carbon dioxide we exhale, they give us more oxygen, they give us a source of food, and in the process, they get to purify that water that they're taking up, because everything that's in that tin can in space is in a closed system. And speaking of closed systems, you may also remember from your 7th grade biology class, this beautiful classical experiment done by Joseph Priestley. This bell jar is like a spaceship. The mouse is the astronaut, right? The little candle in there is the astronaut breathing and whatever other equipment combusting in there. And what happens if you're in a closed container and you're consuming oxygen? It's not a good thing, right? The mouse, in this case, expires. But what Priestley found is if you put a plant in there and you're burning a candle for combustion and the mouse is breathing, they'll be just fine, because the plant is taking up the carbon dioxide, making oxygen, and the little mouse can run around. This analogy, this bell jar is our spaceship, and the mouse is our astronaut. And if we put plants in there, that's our hope for long-term traveling in space. All right, so that's sort of the why. Who cares? All of us, presumably, because we're here interested in space travel. And as I said, this is what's going to make space travel possible. And now I'm going to get to how, and this is a shameless sidetrack into my own work. And the question is, how does gravity affect plants? I'm not going to talk about that very much, except to say it's critical for everything from the overall root shoot axis alignment to subcellular changes that happen inside of cells. But how do we know that gravity actually even affects plants? We know that roots grow down, right? We all learned this in kindergarten. We know that roots grow down and shoots grow up. How do we know it's gravity that does that? You know that because people have told you, but could easily be light, right? Light is on top, makes shoots grow up, and the roots are scared of the light, so they grow down, right? Could be magnetic fields that are making these things grow this way. Who knows? So I'm going to ask my audience here. You're back in the 18th century, 19th century, actually, very early 19th century. Nobody knew. What kind of experiment would you do that would just determine that, in fact, it's gravity that is making these plants grow this way and not something else like light, perhaps?
Different variables that you're changing each one.
So you could do different variables, but let's have one here. I'm going to give you a hint. What does this remind you of, right? Our happy days on the playground. Okay, what happens when this merry-go-round goes around? I'll give you another hint. I'll show you a more exciting playground. So what happens here when this thing spins around? Pushed out, right? Which is mimicking gravity. Right? So if this were gravity, which way is down? Outside or toward the inside of this merry-go-round? So, I mean, we know if I drop something here, gravity is going to make it go down, right? We did this here, would this be going this direction or this direction, which is down, out, right? Exactly right. And you're not the only one that thought of that. Okay. Turns out that Thomas Andrew Knight in 1806 was a farmer. He had plants. He was wondering what the heck is going on here with these roots and shoots. And he and his gardener set up a beautiful experiment with a water wheel, okay, that was acting like a centrifuge. And he set his plants up like this, roots, shoots, okay, and now he's going to spin this. So you tell me what's going to happen. One of these is in the correct alignment. It's going to just keep growing. Which one of these four? You're right, it's this one, okay? Because you told me that this is down, root would keep growing here, right? But he didn't know this, right? We know this. But this one's going to change, right? That one up there, it looks like it's going to be totally backwards. So what happens after they spin this around for a while? We get this image. So this one has continued to grow. The one on top totally had to turn around, right? And so they were able to deduce, yes, gravity. No, they can't see me, but they can look at the slides anyway. So I know people in the Zoom audience have to use their imaginations. And so we see that, and I guess I can use my cursor to point at the slides, that if in this poor plant that has to tie itself up into knots, then it was clear that gravity is having an effect here, not light, because light was uniform over this, right? So great. So we know gravity is critical. Then, I'm sorry? The time lag is on the hours to see something with your eyes without any sophisticated measurements, right? It's on minutes if you have better measurement. But with the water wheel experiment, you can see that in hours. Yeah. If any of you go to the Smithsonian and buy a turntable to play an LP, you can do that experiment at home. Okay. So how is it then that this gravity signal, since we now know it's a gravity signal, is sensed? And shortly after this in the 19th century, lots of German scientists looked at this and they came up with ideas that maybe they're sensing these cells are sensing the differential in pressure. And there's maybe a compression at the bottom of the cell and a tension at the top of the cell. Pfeffer came up with basically the same idea. Charles and Francis Darwin, Francis is Charles's son, were very interested in plant physiology, plant development. They're the ones that realize there's something funny about the tip of the root that seems to be critical for gravity sensing. At this time, animal physiologists had just discovered that invertebrates have these sedimenting extracellular particles that bounce into hair cells that allow them to sense gravity. And so they predicted, maybe we'll find some sedimenting particles in plant cells. And sure enough, shortly after that, these particles were discovered in both shoots and roots of plants, and the starch statolith model of gravity sensing was born. This is what's in all biology textbooks. And the idea is that these particles you can see in the root that are staining sort of dark purple in there are settling to the bottom. And somehow that's how plants perceive gravity. It's a great idea, makes great sense, sort of, as long as you don't worry about the energetics. But there's some flies in the ointment, including, well, there are roots where the starch grains don't settle. They stay right there. In fact, Francis Darwin noticed that already. He commented about that in 1902. There are also plants that respond to gravity very well, thank you, but they don't have statoliths anywhere. There are also, more recently, we've made mutants of plants that don't have statoliths, and they respond to gravity too. So it seems hard to credit that something that can be gone and the plant still senses gravity is a gravity sensor. Nevertheless, this is still what's in all the textbooks, right? So right about 1900 is when this statolith model came up. Just a couple of years later, there's this great book published on the physics and physiology of this giant, this plant that has giant cells about this big that turns out respond to gravity, at least according to Ewart. So at this time, we thought, not in 1903, a little bit later than that, we were reading this literature, thought this would be a great place to start looking, because here is a cell that apparently responds to gravity, doesn't have statoliths. Let's see if we can figure out what's going on. And the beautiful thing is you can cut these cells and make a single cell. So that image you have at the bottom is one single cell. And the gravity response, I don't want to go into many details, but there's a polarity of cytoplasmic streaming. It's fascinating from a lot of perspectives. But I'm just going to say, if you put the cell horizontal, there's no gravity response. It's streaming right and left at the same rate. If you have a vertical cell, it turns out that it streams down about 10% faster than it streams up. That's what Ewart reported. That's what we found as well. And at that point, we thought, well, big deal. Everything goes down faster than it goes up. This is probably a physical response. Remember, this was on the physics and physiology. And so maybe it has something to do with the viscosity of the cell. So I was going to do an experiment where I was actually going to centrifuge a cell and then tie it off and make a light cell and a not light cell. And didn't have time that day to do it. So I just did the control experiment where we just ligated the cell. So there in this final image here, you can just take a piece of string, tie a knot carefully, and then you can cut the end off a cell. Turns out when you do that, this cell, when you put it up vertically, streams up and down at the same rate, just like a horizontal cell. That's not just a physical response. This is under physiological control. So then you say, well, how can this cell be sensing gravity? There are no statoliths, right? So we thought, all right, maybe this cell is doing what very first people who suggested this. The protoplast is settling within the confines of the cell wall, or the extracellular matrix for all of you animal physiologists. And there's a compression at the bottom of the cell and a tension at the top of the cell. And that's the way the cell senses gravity. Okay, so if that's possible, we had to make a model, see that we were within the realm of physical possibility. Danger, here comes a formula, but don't worry about it. Really, what we're saying here is that the gravity response, what we're predicting, if our model is correct, should be related to the force of gravity times the volume of the cell, and then the difference in the density between the protoplast and the external medium. And then there's that little D at the end, which I'm going to skip now. If anyone wants to ask questions later, we can do that and talk about that. All right, but this immediately, you see a minus sign in the formula, and you immediately say, here's a testable hypothesis, right? So if this model is correct, if we increase the density of the external medium, so it's greater than the density of the protoplast, we ought to see a reversed response, right? So if we take our little plant cell and we drop it in normal pond water within the confines of the cell wall, you're going to have to pretend like this cylinder is the cell wall and this is a protoplast. It's sinking to the bottom. But if we change the medium so that it's now more dense, when we put this in, hopefully it's going to float. And it does, okay? And so if this were the cell, we'd have a compression at the top and a tension at the bottom instead. Okay, so that's the model. And I'm very happy to say, when we do that experiment, we find we reverse the gravity response in care. Okay, so even if there were microscopic, invisible starch grains or anything that were in there, it wouldn't matter because they'd still be sedimenting to the bottom inside of our protoplast, right? but the whole protoplast has become buoyant, right? So we're excited. That's great. Okay, so here's a cartoon of what we said there. In the normal conditions, in pond water, the protoplast is more dense, it settles to the bottom, and we get this normal response with streaming down. That's what the long arrow is supposed to mean, is faster than streaming up. In the case where you reverse the condition, you make the external medium more dense, you get streaming up faster than you stream down, right? That's both a prediction, and it turns out that's the result that we found. Okay, that's pretty exciting. But then immediately when we published that, people said, well, you know what? Plants are not, these cells are not plants. Instead, you need to do something with higher plants, with roots. So I said, fine, let's look at this root. Darwin told us that the tip is where gravity sensing happens. That's right. There are those starch grains in there that may or may not sediment. Okay, so why don't we just do the same experiment with roots? Great idea. So the experiment would be, normally we'd see the little starch grains sedimenting to the bottom, as you see in that image. You'd have a tension at the top, compression at the bottom of the cell. If we then put this cell in a more dense medium, we would expect the protoplast to become buoyant. Stabilis are still sedimenting at the bottom, but you'd get a compression at the top of the cell, a tension at the bottom of the cell, and you'd get a reverse gravity response. That sounds great, but then we have to remember chemistry and what life is made out of. And life is made out of all those elements at the top of the periodic table, and all those things at the bottom of the periodic table that are dense are death, right? They all are used for, sometimes commercially, for killing cells, but it turns out they're all toxic, all these heavy metals. So this is a real challenge to doing the experiment. Luckily, after a long time of searching and trying to think of how to do this, we found this caged iodine chemical, which we don't need to go into any details except to say it's very dense and it's mostly non-toxic, right? So we can now take a rice root that has starch grains. I don't know if you can see the starch grains here, but they're in the bottom of this balloon. Normally, it would sink. If you put it in the medium that was okay for Cara, it still sinks, but now we can put it in an even more dense medium that's non-toxic, and it's floating. And so we ought to be able to do the experiment. All right, so let's see what happens when we do the experiment. Here are rice roots sitting in APW. That's a fancy word for artificial pond water. 300 minutes. So there's your time scale. We get a very clear gravity response. They've all grown down to gravity. And then as we increase the concentration of this octoprep that's in this beaker, we find less curvature, and eventually, oh yeah, they went below that blue line. That means they're growing up. Okay, so we've done it. We've shown that we can support this gravitational pressure model that we've developed, except for one thing. I said it's mostly non-toxic. So we'll see if this video goes. These are the roots themselves, and what you'll see is they're not happy at this point. You saw how far they grew in the first slide. They're confused. There's some growing up, there's some growing sideways towards you, there's some growing sideways and up. But the main thing you notice is they're not growing very much. And so even though they're growing down on average, they're not healthy. They're not happy. There could be secondary issues here, and we're not really affecting the gravity sensor. So I said, oh, shoot, now what do you do? And this was a little impasse for a while, till we started thinking about, light. I mean, gravity isn't the only thing that plants respond to. Light, as I suggested early on, is another one. And it turns out that these roots, if you shine blue light on them, they grow away from the light. If this is the light, the roots are going to grow away in the opposite direction, right? Because actually roots do want to go underground away from the light, more or less, right? So if we put a horizontal, if we put a root that's perpendicular to, parallel to the vector of gravity and shine a light from the side, gravity is going to want to make the root grow down. The light is going to want to make the root grow out here, right? And so there's going to be a tension between those forces, and you'll get some angle. Then what? You can change the density of the external medium, maybe this much. So it's not toxic, but it's enough. And what would you predict? Would you predict a bigger effect of gravity or a less effect of gravity when you increase the density of the external medium? I'm asking my audience of experts. Yeah, so I'm shining a light here. I've got the root going here. Normally, it's going to be at some angle like this. If we increase the density of the medium, and if our model is correct, that means we're going to decrease the effect of gravity. It's going to go out more in this direction. Let's see if that happens. All right. So here we have, it turns out these are blind to red light, more or less. If anything, you're going to see this is growing maybe a little bit towards the red light. You can see the arrow is showing where the light is coming from, but they're growing. They're not doing a whole lot. Now, if we look at what happens in blue light, you can see where the blue light is coming from. Gravity's still pointing down. If we watch what they do, I don't know if this video started. Okay, how many times have you seen the video not run when you wish it would run? Okay, you're gonna not see it, but it's growing down and curving away from the light. It didn't go very far. I'm going to just go to the next one and see if it will play. This is the one where the more dense solution, okay? And they're clearly growing away from the, I'm sorry, I don't know why the other one didn't do anything. But what I want you to notice is these were not sad little roots. These roots are actually growing pretty rapidly, but they bent away from the light more, right? So for those of you who want to see the data, presented in a graphical way, you'll see that in artificial pond water, they curved a certain amount, about 15, a little more, 16, 17 degrees. When we increase the density with either sucrose, which by the way is a magic chemical in here today, or this Optiprep, which isn't because it costs $100 a milliliter, you get the same results, okay? So this is actually, this is like a neat little parlor trick, but this is actually a profound thing. What this means is that, we increase the density of the external medium, we can inhibit and eventually reverse a gravity response, okay? If we do this experiment with the blue light, we can inhibit the gravity response without affecting growth, right? So there's no indirect effect going on here, right? So these are consistent with our gravitational pressure model that, this cell is sensing the differential tension, compression at the bottom of the cell and tension at the top of the cell under normal conditions. And it is inconsistent with the sedimenting starch grain model because those starch grains are sedimenting. No matter whether you're holding this up in the air, sticking it in any medium, they're still at the bottom of that protoplast. So if that were the critical signal, this experiment, these results wouldn't have happened. So I take this, even as a scientist, as incontrovertible evidence here for this. And I'm delighted to say after we presented this last summer, we're making some traction here. We're getting some traction. So you may ask, as an engineer, why the hell are all these starch grains in cells in if they're not sensors? What are they doing? Okay, so you have to cast your mind back to that formula we had for the gravity response. V is a big thing, volume, right? Kara, those cells we were working with without starch, they're this big. They're more than 1 million times bigger than one of those columella cells in the roots. So if you're going to make enough energy to be within the realm of physical possibility to be doing anything, right? We got to make at least, like, for my scientists here, 10 to the minus 19th, 10 to the minus 20 joules for something to be sensed. What do we need? We need something to make the cell dense. We need ballast. And that's what I think these starch grains are. They are ballast, right? So then V is critical. And if V is small, then you've got to make that difference between the protoplast and the external medium be bigger, okay? And that's what the starch grains are for. And that explains perfectly why the mutants that don't have starch grains still respond to gravity, but with lower kinetics. It takes longer because, right, makes perfect sense. It actually supports all the data that we know. So that's pretty nice. All right, so let's go away from there and think about going into space again with plants. Now that we know our plants will know whether they're in space or not because of sensing the gravity. And we look at all the space missions that we've had, and you said you had posters on this. But the point I really want to make here is throughout Mercury, Gemini, Apollo, these are really short trips with 1, 2, or 3 people on board the very small spaceship. They didn't have time to have plants. They didn't need plants because they were going out and coming back right away. Okay. I don't have the ISS up here, but you know, since the 70s and today, we've had we have had missions to space. They haven't been exploration missions. We've been doing a lot of work in low Earth orbit is what they call where the ISS is. And there have been lots of experiments with plants, but they really haven't needed plants because they have constant traveling coming between the Earth and the ISS. And so they can use chemical means for regenerating oxygen. They can bring up food packets, right? Yes, they've grown little lettuces, but it's been, you know, more for fun and for psychological well-being that they've had plants up there. Okay, but now with the Artemis program starting and the plan to go to the moon, to have an orbiting station around the moon to prepare for trips onto Mars, we're not going to be getting refueled for oxygen. We're not going to be getting refueled for food as much. And certainly when we go off to Mars, we're not going to have that. Okay, so plants now become critically important for the reason that we showed in those slides at the very beginning. Okay, I just want to remind ourselves, though, that getting to the moon is not an easy thing, right? Here's an artist's rendering of what we hope is going to happen. SpaceX's Starship landing on the moon, maybe in the next year or two. That would be nice, going to the South Pole of the moon, which will be a very interesting thing scientifically, as well as for future exploration. So this is what we hope will be showing will happen with our missions. The Chinese are about the only people who've successfully gone to the moon since we did. They had their lander. They actually brought some biology experiments. The first biology experiments were done by Chinese. It lasted only a couple of days before they lost power, and then lunar night came and everything froze and died. However, they did, you'll have to take their word for it. This is their image of what was growing inside of their lander. And this is a cotton plant. So the first plant grown on the moon was cotton, okay? I think we'll decide later that's probably not what we're going to take up into space, but that's what they got. And it lasted for this one day, and then it died the next day because everything froze. Okay. The Japanese tried to get to the moon this year. They landed pinpoint accuracy, but upside down. And so, you know, the people in charge of the mission for getting it to the right place get an A+. The people in charge of making it work once it landed need to go back to the drawing board. But at least that's better, right? We've had our colleagues from Russia and India recently tried to land, and those were just unsuccessful events. So this is not an easy thing. Okay, it was a success. Okay. So we have really ambitious plans for Artemis and beyond, right? We've got sort of reading across here is sort of a timeline as well as an artist's view here, where we're going to make an ever more elaborate orbiting launch pad to go on to further things. And then on the moon, develop ever more elaborate perhaps living quarters for people. And so we are definitely going to need plants on the moon. And then when we go to Mars, which could be up to one of the plans is an 850-day trip to get to Mars, circle, and come back again. We're going to not be resupplied during that trip. And so we better be sure we have something that gives us oxygen, something that uses up our carbon dioxide, something that can purify our water, and something that can give us food. All of those things we remember from 8th grade biology can be done by plants, right? And only done by plants. So why do we need them, right? Food, nutraceuticals. We haven't really talked about what happens when you're in space, but there's a lot of damage that astronauts take. They take a lot of hits in space, a lot of oxidative stress, and their plants, luckily, and I call these nutraceuticals, right, can have antioxidant properties, and that can be a great benefit. Besides just eating food. Oxygen, obviously, we need as well. And it turns out that for emotional well-being, it's great if you're going up for 10 days and coming back, but if you're going for 800 days, turns out that plants calm astronauts down and make them feel better. And we want our astronauts to feel good when they're on this long mission in not great conditions. All right, what kind of plants are we going to take? Well, this is actually the room in this Mars analog mission that's going on now, where they're going to decide. You can see it's empty there. They haven't put anything in. First of all, we might think about what are we going to grow plants in? Are we going to take soil up? Probably not, right? Payload is very valuable. Hauling Earth, probably not going to be good. On the moon, are we going to use lunar regolith? Probably not. That is pretty toxic stuff. It's like mine dump tailings. Trying to grow plants in that is very difficult. I had a demonstration for you, but everything was dead in it, and I thought that'd be too depressing. So let's just say I got lunar simulant, and all the little plants we put in them did not do any better than the plant on the Chinese lander. All right, so Martian regolith, we don't know for sure, but we're pretty sure it's just as bad. So, you know, we know there's water on the moon. There's ice anyway on the moon, and so we can make water. And maybe we'll have water on Mars. But are we going to use that soil? I don't know. So probably it's going to be none of the above. We're probably going to be doing some hydroponic system and maybe just take some structure along to hold things. All right. So, but what are we going to grow then? Right. So we decided it's going to be hydroponics. What are we going to grow? Well, what should we grow? You tell me, my panel of experts here. What should we grow? Yeah, potatoes. Corn, yeah. So that's great. Potatoes are delicious, so is corn. But there's a corn, there's a lot of stalk and roots that you can't eat, take up a lot of space. Plus, corn takes a while before it grows. Yeah, so I can tell the way you're going. We're trying to minimize the inedible part, maximize the edible part. And so, what has NASA been looking at? Well, there's wheat. That's basically a mini corn, right? Probably that's not going to go, right? We can grow it, but I'm not sure we're going to be doing that anytime soon because you just have those grains and most of this plant is inedible, right? Okay. Here we've got mustard, we've got red lettuce, we've got green lettuce. Look at that. This is growing in a hydroponic situation. They're injecting some micronutrients there for the plant. This is looking pretty good. Maybe kale, right? Again, most of this stuff is edible, just not the roots. Okay. These are all the things that NASA is working on right now and are growing in space. None of these are my favorite. I'm going to give you my favorite here, and that is Wolfia. Okay, Wolfia is, you all know duckweed. You've seen it growing on ponds. This is duckweed without roots. So this is a plant that has no stem, has a tiny little shoot with leaves and no roots. It's 100% edible, grows very rapidly, has a very high rate of photosynthesis, so it makes a lot of oxygen, consumes a lot of carbon dioxide, has been used for water purification, and it can be used for that as well. And it turns out not only is it edible, but it has enormously high concentrations of vitamins, of useful minerals, and large numbers of antioxidants for oxidative stress. So this is my personal favorite. I don't know that there are many menus, many recipes set up for this, but Wolfia, that's the base. It's better than Tang, right? Which those of us remember, right? The space food. So this is what I think is going to be the future of food in space. And eventually, when we can make soil that works, then we can grow our potatoes, right? Then you can grow your rice. And, to make people happy, we can grow a few red peppers or hot peppers as they have done on the ISS. And then finally, the thing that I think we'll probably also do is every once in a while grow something purely for beauty and purely for state of mind, like these zinnias that Scott Kelly rescued when they started getting fungal contamination on them. I nursed them back to health, made this beautiful image from the cupola there looking out over the earth on Valentine's Day. So, right, just a few years ago. So on that happy Valentine's Day note, I would like to thank you in the audience very much for your attention, and thank for the Zoom people in Zoom land for their attention. I'd be delighted to answer any questions, assuming that we have time, and we have at least a little time.
Thank you. I'm gonna take this outside.
Okay, take it outside. Thank you.
Yeah, Dina is doing that.
Okay.
So I'm moderating this part. I've been texting you, but I wasn't
Oh,
sure.
you have? Sorry.
No, I was texting Samita.
Okay.
So I've been given a few questions. One of them is, could you share some of your most surprising findings from your experiments with plants in microgravity environments?
So the beautiful thing is I'm always wrong when I make a prediction. When I was doing this work, someone came and I guess they wanted to do an interview, and they said we sort of went through the history of how we did this, and the way we present like today is never the way science actually happens, right? This is what happens after you figured out all your mistakes. And so the beautiful thing is there's so many times when I've made a prediction of what would happen. It was totally the opposite. And I was all crestfallen. And then you look at the data and say, oh, that makes perfect sense if you look at it this way. And you keep going. So I would say for me, it was just the huge numbers of mistakes and the way mistakes can turn into real strengths. If you accept them, that what you thought was wrong, and then right, you think about it and see where you can take it from there. I guess this whole notion of combining different environmental stimuli, light and gravity, and being able to tease out the answer to a question that you couldn't do with looking at one individually was I guess a beautiful thing, being able to make a thought experiment turn into a real experiment and get results.
Awesome. There's a question from Robert Baldaiga. I hope I'm pronouncing that correctly. Are there any opportunities for meaningful citizen scientists here? Student projects?
So you know what? That's a great question. And the answer is yes. So one of the things I've done in the last few years is sit on panels for NASA, thinking about scientific merit of different experiments that are proposed for South Pole of the Moon, for ISS, or for this yet unbuilt rotating space station. And clearly, there's got to be work on seeds on the moon, plants growing on the moon, and the question of which ones to choose. This is a great citizen science opportunity, and there's gonna be send your seeds to the moon. This is something that will be coming. I don't know when, but we'll have to have trips, Artemis landing on the moon before then. So this is going to be something choosing why. Is it because of nutritional value? Is it because of cultural value? Is it because of some unusual biological aspect about these seeds? Right. So there are so many things that most plant physiologists, they work on 5 or 6 plants and that's it. So there's huge scope for citizen science in that idea of just choosing what might go. And then, there's always ground control. Every time an experiment is launched into space, there's a ground control experiment, just like there was with this Chinese lander in their cotton. Their cotton on the ground grew a lot better than the one on the moon because they didn't encounter lunar light. And this is something that I think schools can, actually they are to some extent. There are a number of schools in South Florida near NASA there that are doing work that's supporting flight missions. And I think that can be expanded enormously.
Well, that's wonderful for that. Thank you so much. I don't think we have time for another question, although I did want to point out on Samita's behalf that the Chandrayaan-3 mission successfully landed in the southern polar region of the moon on August 23rd.
Yes, I'm sorry. It landed. The Russians tried to sneak in front of them by launching later, but trying to land early, and that didn't work. So Samita did point out that, and that's quite correct. We just don't have experiments yet from them, which is
no, this is great, and I think from the perspective of trying to understand how even things like human reproduction might work in microgravity, understanding plants first, I think, is a really important step.
Well, it is.
I know it's different, but on the cellular level, it's similar.
It's different on the cellular level. It's similar. There's one of the things I've been working on recently is not how plants sense, but how they don't sense their environment. So anesthesia. It's astonishing. We give anesthesia probably millions of times a day when people are going to surgery. And most of the time we have no idea what that drug is doing, right? We have no idea what the mechanism is.
Wow.
And I think that plants are going to give us an answer.
Interesting.
Not too distant future.
So
I think your point is well made.
Thank you so much, Mark. We really appreciate it.
Thank you. It's been a pleasure. And I hope everyone enjoys the rest of the conference. Thank you.
Thank you. And everybody, I'm going to be putting us back into waiting mode, and we'll be getting set for our next presenter, Neve Shah, at 10 a.m.